Picture yourself walking into a lab, not a clean white room full of humming servers, nothing like the computer you're imagining. What you find, hanging from the ceiling, is a chandelier. Gold. Tier upon tier of gold plates and gleaming copper, and hundreds of hair-thin cables spiraling down through it like the strings of some impossible instrument. It is beautiful and it is strange, and it is doing something no ordinary machine can. Because sealed inside the heart of that chandelier, behind its shields, in the dark, is a chip smaller than your fingernail, held at a temperature colder than the empty space between the stars. Colder than anywhere in the natural universe. And that frozen fleck of metal in that golden cage is one of the most powerful computers of its kind on Earth. Today, we open the cage. Today, we ask the question we've dodged for 9 whole episodes. Not what a quantum computer does, but what one physically is.
And it's the right time to finally ask it, because you've earned it. For 9 episodes, we've been living in the world of ideas. Qubits, superposition, entanglement, interference, the whole beautiful machinery of it. All of it, honestly, a bit abstract. Arrows on spheres, amplitudes cancelling, and a listener would be forgiven for quietly wondering the whole time, yes, but where's the thing? What is any of this actually made of?
That's exactly it. We've been saying qubit the way you'd say engine, as if everyone knows what's under the hood, and I realized I don't. When a lab says we have a 50-qubit machine, what did they build? What would I be looking at if you sat me in front of it?
Here's the answer that surprises almost everyone, and it's where the whole story of tonight begins. There isn't one answer. If you walked into 5 different laboratories and asked to see a qubit, you would be shown 5 completely different things. In one, a tiny loop of metal on a chip. In another, a single atom floating in a vacuum, pinned in place by invisible fields. In a third, a speck of light. These aren't 5 brands of the same product. They are 5 genuinely different physical objects, each one being asked to play the same role.
Wait, so qubit isn't a kind of stuff, it's more like a job.
That's exactly the shift I want you to make. A qubit is a job, not a material. The job is, be a quantum system with 2 clean states you can point between. The 2 poles of that sphere we drew back in the beginning, and hold that delicate in-betweenness long enough to compute with it. Anything in nature that can do that job is a candidate. And it turns out nature offers you a whole menagerie of candidates, each with its own personality, its own gifts, and its own fatal weakness.
A menagerie. So this is less a factory floor and more a zoo.
A zoo is precisely the word people use. The quantum hardware zoo. And here's what makes it such a wonderful moment in the history of the field. Nobody yet knows which animal wins. We are living through the rare stretch of a technology's life where the fundamental question, what should this even be built out of, is still genuinely open. Imagine the early days of flight, when some people were strapping on wings, and some were building balloons, and some were bolting engines to kites, and nobody could yet tell you which idea would carry a person across an ocean. That's where we are. Tonight is the tour of the wings and the balloons. The one problem every animal in the zoo is fighting.
Before we start opening cages, is there a thread? 5 different creatures is a lot to hold in my head. Is there one question all of them are really answering?
There is, and if you hold on to nothing else tonight, hold on to this. Every single platform in that zoo is one team's answer to the exact same impossible demand. The demand we ended up staring at a couple of episodes ago when we talked about noise.
Right, the fragility. That episode genuinely rattled me. The whole cruel paradox of it. A qubit is powerful precisely because it's so exquisitely sensitive, and it's doomed for exactly the same reason. The tiniest whisper from the outside world, a stray photon, a breath of heat, and the superposition is gone. The environment reaches in and, without meaning to, effectively measures your qubit, and the magic collapses.
You've got it word for word. And remember the shape of the demand that left us with. You need two things at once that seem to flatly contradict each other. First, you need to isolate your qubit from absolutely everything, seal it away from the whole universe so nothing can accidentally disturb it. And second, at the very same time, you need to reach in and control it with immense precision. Nudge it, flip it, make two of them talk to each other, and then read the answer out. Perfect isolation and perfect access. A locked vault that you also need to reach into 1,000 times a second.
A soundproof room that you're also constantly shouting into. Those two things want opposite architectures.
They want opposite everything. And that, right there, is the whole engineering problem of building a quantum computer, compressed into a sentence. Every platform in the zoo is a different negotiated settlement between those two enemies: isolation and control. Each one says, in effect, here is where I'll buy my quiet, and here is the price I'll pay to still get my hands on the thing. When you understand what each animal chose to sacrifice, you understand the animal. So that's our lens for the whole tour. For each one, I'll give you the gift, and I'll give you the one honest wound. Deal?
Deal. Open the first cage. And I'm guessing we start with the one in the golden chandelier because you've been dangling it since the top of the show. The circuit that pretends to be an atom.
We start there because it's the animal most of the famous machines are built from. The one you've seen in the photographs, even if you didn't know what you were looking at. It's called a superconducting qubit. And the strangest, loveliest thing about it is this. It is not a naturally occurring quantum object at all. It's a circuit. Something a person designed and printed onto a chip, out of metal, like any other bit of electronics.
Hold on. Everything we've talked about, atoms, photons, spins, those are nature's own tiny quantum things. You're telling me you can just build a quantum object out of ordinary circuitry?
You can, and it's one of the small miracles of the field. Here's the trick. Take a loop of metal and cool it down until it becomes a superconductor, a state where electrical current flows with no resistance at all, the electrons moving as one single, unified quantum wave rather than a jostling crowd. Now you've got a whole circuit behaving as one coherent quantum thing. Put a very particular little interruption in that loop, a paper-thin sliver where the superconductor is briefly broken, and something magical happens to the circuit's energy. Instead of being able to hold any amount of energy it likes, the way an ordinary circuit can, it's now only allowed to sit on specific rungs. A ladder of allowed energies.
Rungs, like the energy levels of an atom.
Exactly like the energy levels of an atom. That's the whole point, and it's why people call these things artificial atoms. A real atom has that ladder of allowed energies because of the quantum rules governing its electrons. This circuit has a ladder for its own reasons, but a ladder is a ladder. You take the bottom rung and call it 0. You take the next rung up and call it 1. And now you deliberately ignore all the rungs above. You've got your two clean states. You've got a qubit, one you drew yourself on a computer and had fabricated in a clean room like a microchip.
That's genuinely wild. So instead of hunting the universe for a good two-level system, you just manufacture one to spec.
And that is superconducting qubits' greatest gift. They're built, not found. You can design them, tune them, wire them together with printed connections, and manufacture them with the same kind of technology that makes the chip in your phone. The entire trillion-dollar knowledge of how to pattern metal onto silicon, you get to borrow all of it. That's an enormous head start. And there's a second gift on top. They're fast. You control them with microwave pulses, the same kind of microwaves as in your kitchen, just exquisitely shaped, and a single operation takes something like a few billionths of a second. Blisteringly quick, you can do a great many operations before the state ever fades.
Built to spec, And fast. That sounds close to having it all. So where's the wound? What did they sacrifice?
Two things, and they're related. First, because this qubit is a big, sprawling, man-made circuit, rather than a tiny natural atom, it has a lot of surface exposed to the world. It's a large object by quantum standards, almost visible, and largeness means the environment has 1,000 handles to grab it by. So it's noisy. It holds its delicate superposition for a heartbreakingly short time, measured in millionths of a second at best, before the world creeps in and wipes it. That's the fragility problem biting hard.
So the very thing that makes it easy to build, being a big engineered object, is what makes it leaky.
You've put your finger right on the tension, and the second part of the wound follows from the first. To buy back some of that quiet, to starve the environment of the heat and the stray radiation that would otherwise destroy the state, you have to take this chip and make it cold. Not fridge cold, not winter cold, colder than the deepest, emptiest patch of the cosmos. And that is what the golden chandelier is for. The coldest place you'll ever hear about.
Okay, take me inside the chandelier, because in my head it's just a pretty sculpture, and I don't actually understand what it's doing.
Then let's climb down through it, because it's one of the most beautiful pieces of engineering humans have ever built, and almost nobody knows how it works. The proper name is a dilution refrigerator, and the whole golden structure is, believe it or not, a fridge, but one unlike any you've met. Think of it as a staircase of cold, a stack of plates, each one, as you descend, held colder than the one above it.
A staircase where every step down is colder than the last.
Every step. The top plate might be merely very cold, the kind of cold you'd get from liquid nitrogen, chilly enough to shatter a rose. Step down, colder. Step down again, colder still. And each stage's job is to protect the stage below it, to intercept the heat leaking down from the warm world above, so that the next plate can go colder yet without being disturbed. By the time you reach the very bottom plate, the one cradling the chip, you have arrived at something extraordinary. Roughly 1/100th of a degree above absolute zero.
1/100th of a degree above absolute zero. Help me feel that. Absolute zero is the coldest anything can possibly be, right? The bottom. There's no colder.
The floor of temperature itself. The point where all the ordinary jiggling of matter, the restless heat motion in everything around you right now, quiets to the barest whisper the quantum rules will still permit. Nothing can go below it, and the bottom of that chandelier sits just 1/100th of a degree above that floor. Now, here's the fact that always stops people. How cold is deep space, the great void between the galaxies, as far from any star as you can get?
I'd have said that's about as cold as it gets. Isn't empty space basically the definition of freezing?
You'd think so. But deep space still glows, ever so faintly, with the leftover warmth of the early universe, that faint afterglow left over from the cosmos's fiery birth, and that keeps it at a couple of degrees above absolute zero, which means the bottom of that golden chandelier in a lab on Earth is colder than outer space. Considerably colder. When that fridge is running, the little chip inside it is very plausibly the coldest cubic inch in the entire universe. The coldest anywhere. Colder than any natural place the cosmos has ever made.
That genuinely gives me chills, no pun intended. We built the coldest spot in creation, on purpose, to hide a fleck of metal from the world.
To hide it from the world. That's exactly what the cold is for. Heat is noise. Heat is the environment's 1,000 fingers. Every degree you strip away is a finger you pull off the qubit. So the cold isn't a quirk. It's the whole isolation half of our bargain made physical. And now you understand the chandelier. Those tiers are the staircase of cold. The gold is there because gold is a superb conductor of heat, and it doesn't tarnish, so it moves warmth around cleanly and never corrodes. And those hundreds of delicate spiraling cables are the control half. The wires carrying the microwave pulses down from the warm room at the top, all the way to the frozen chip at the bottom, so you can reach in and compute.
So the whole sculpture is the two enemies made visible. The tears and the gold are the isolation. The cables threading down through them are the control. The chandelier is literally the compromise, hanging from the ceiling.
You've just read the machine like a poem, and you read it correctly. Everything in that structure is either buying quiet or buying access. And notice the cost of it. This towering cryogenic cathedral, all of it, exists to keep a chip the size of a thumbnail cold enough and quiet enough to hold a thought for a few millionths of a second. That's the deal superconducting qubits struck. Fast and buildable, but so leaky they must live at the bottom of the coldest well on Earth.
All right, that's one animal, and I feel like I've properly met it. Who's next? Because you promised me something that isn't a circuit at all. The atom that nature already perfected.
Next is, in a sense, the opposite philosophy. If the superconducting people said, "Let's build our qubit," this next tribe said, "Why build one when nature already perfected the finest two-level quantum systems there could ever be, and scattered them freely across the whole universe?" These are the trapped ion machines, and the qubit here is a single atom, a real one.
A single atom. Not a circuit pretending to be an atom, an actual atom.
An actual atom with one small alteration. You gently strip off one of its electrons so it carries a bit of electric charge. A charged atom is called an ion, and the charge is the handle, because anything with charge can be pushed and held by electric fields. So you build a little trap, an arrangement of electrodes humming with carefully tuned voltages, and it creates an invisible basket in empty space. You drop your ion into that basket, in a chamber pumped down to a vacuum emptier than the space around the moon, and it just floats there, held in nothing, touching nothing. And it will hang there, suspended, for hours, days even.
There's something almost tender about that. A single atom, cupped in mid-air by invisible hands, in the emptiest room ever made.
It is tender, and it's also the whole trick. Remember our two enemies, isolation and control. Well, floating in a vacuum, touching nothing, is about as isolated as a piece of matter can get. So how do you get your two clean states? You pick two of the atom's own natural energy levels, its real God-given ladder rungs, and call one 0 and one 1. And how do you control it? Reach in and flip it? With light. You hit it with exquisitely precise laser beams. A pulse of laser light of just the right color can lift the atom from 0 to 1, or set it spinning into any superposition in between, with breathtaking accuracy.
Lasers as the fingers. So the control here is a beam of light instead of a wire.
A beam of light, and that reaches in without any physical cable ever touching the atom, which keeps the isolation gorgeously intact. And now here's the gift, the thing that makes people who love trapped ions absolutely evangelical about them. Because these are real atoms chosen from a single element, every one of them is exactly, perfectly identical. Not manufactured to close tolerance, genuinely, fundamentally the same as only two atoms of the same element can be. Every calcium ion in the universe is a flawless copy of every other. And floating there in near-perfect isolation, they are astonishingly quiet. A trapped ion can hold its delicate superposition not for millionths of a second, but for whole seconds, sometimes minutes.
Minutes? Against the superconductor's millionths of a second? That's not a small edge, that's a chasm. Why would anyone use anything else?
Because, and you knew this was coming, there's the wound. Two of them again. The first is speed. Those laser operations that are so beautifully precise are also comparatively slow. Where the superconducting circuit does its thing in billionths of a second, coaxing an ion with a laser takes more like millionths of a second, 1,000 times more ponderous, roughly. The ion holds its thought far longer, yes, but it also thinks far more slowly. So it's not simply the winner, it's a different balance of patience against pace.
The tortoise and the hare, almost. The circuit is a frantic sprinter with a terrible memory. The ion is slow and thoughtful, but never forgets.
That's a lovely way to hold it. And the second wound is the harder one, scaling. Here's the beautiful problem. Because all your ions sit in one shared trap, they're all jostling in the same electric basket. And that means every ion can be made to feel every other ion. They can all talk to each other directly. For doing the actual computing, for making qubits interact, which we called entangling them, that's a dream. Everyone's in the same room, everyone can shake hands with everyone.
I'm hearing a but the size of a house.
But cram more and more ions into one trap, and that shared basket becomes a nightmare to control. Picture a line of marbles in a shared groove. A few, and you can address each one with a laser cleanly. But a very long line, all coupled together, jostling as one wobbling chain. It becomes fiendishly hard to speak to just one without disturbing its neighbors, and the whole system gets harder and harder to keep in hand. So the very thing that makes ions such wonderful conversationalists, everyone in one room, is exactly what makes it so hard to build a big room. That's their honest wound, sublime quality, real difficulty getting to large numbers. Tweezers made of light.
Okay, so the circuit is fast but leaky and needs the deep freeze. The ion is pristine but slow and hard to scale. I'm starting to really feel your different bets point. Nobody's holding a winning hand, they're all holding different hands. Who's third?
The third is a close cousin of the ion, and it's one of the youngest and most exciting animals in the whole zoo. It came from a wonderful question someone asked. Those trapped ions are marvelous, but wrangling their electric charge in one shared basket is what makes scaling so painful. So what if we used neutral atoms instead? Atoms with no charge at all. Then they don't all shove each other around through a shared basket. But that raises an obvious problem.
Sure, if the atom's got no charge, you've got no handle. You said the charge was the whole grip. How do you hold something with no handle?
With light. This is my favorite bit of physics in the whole episode. It turns out that a tightly focused beam of laser light creates a tiny point where a neutral atom, if it drifts near, gets gently pulled into the brightest spot and held there, trapped in the focus of the beam like a seed caught in the pinch of a pair of tweezers. They're actually called optical tweezers, a tweezer made of nothing but focused light, holding a single atom.
Tweezers of light? That's absurd, and I love it. So you pick up single atoms with beams of light?
One atom per tweezer. And now the gift reveals itself, because light is easy to split and steer. Take one laser beam, pass it through the right optics, and you can split it into hundreds of tweezers at once, arranged in any pattern you like. A neat grid, a honeycomb, whatever you please, and drop a single atom into each one. You suddenly have a whole orderly array of hundreds of identical atoms hanging in a vacuum, each one a qubit, laid out in a pattern you designed. And better still, because the tweezers are just beams of light, you can move them. You can pick atoms up and physically rearrange them mid-computation, carry one across the array to go and interact with another. It's flexible in a way the rigid printed circuits and the shared ion basket simply are not.
So this is the platform that cracked the scaling problem the ions were stuck on. Hundreds of atoms, laid out however you like, rearrangeable.
That's the great promise, yes. The scaling and the flexibility are the gift. But now I have to be honest about the wound, and here it's a subtle and interesting one. If the atoms are neutral and just sitting there minding their own business in their separate tweezers, they ignore each other. They barely feel their neighbors at all. which is wonderful for storing information quietly, but useless for computing, because computing needs them to interact, to entangle, to shake hands. So you need a switch, a way to make two quiet, standoffish atoms suddenly feel each other powerfully, on command, and then go quiet again.
And is there such a switch?
There's a gorgeous one. You take an atom and hit it with a laser that kicks one of its electrons up into a wildly, absurdly high orbit. So high the electron is now looping around at a colossal distance from its own nucleus. An atom bloated up like this is called a Rydberg atom, and it becomes a giant, puffed up thousands of times its normal size. And a giant atom, with its electron way out at the fringes, reaches across and feels its neighbors enormously strongly. So, leave the atoms small and they ignore each other and hold their state in peace. Puff two of them up for an instant and they interact ferociously and become entangled. Let them shrink back and they're quiet again. That's your switch, on and off, at will.
That's such a clean idea. Puff them up to make them talk, shrink them down to make them shut up. So, what's the catch?
The catch is mostly that this animal is young. It's the new arrival at the zoo, and it hasn't had the decades of refinement the others have had. There are rough edges. Sometimes an atom simply goes missing, falls out of its tweezer mid-calculation, and now there's a hole in your array where a qubit used to be. And those puffed-up giant states, for all their usefulness, are themselves delicate and open their own new avenues for error. The promise is enormous and the progress genuinely startling. But it's the least mature of the serious contenders, and maturity is a thing you can only buy with time. That's its wound. Dazzling potential, still growing up. Qubits you could hold to a candle.
We've had a circuit and two kinds of atom. You told me at the top that in one lab you'd be shown a speck of light. I have been waiting patiently. How on earth do you make a qubit out of light?
This is the animal that breaks every rule I've given you so far, and it's wonderful for exactly that reason. The qubit here is a single particle of light, a lone photon, the smallest possible pinch of a light beam. And you store your information in some property of that photon. For instance, is it wiggling side to side or up and down? Physicists call that polarization, but you can just think of it as the little orientation the light is holding. Call one orientation 0, the other 1, and any blend of the two is your superposition. Your qubit is now flying through space at the speed of light, because it is light.
Hang on, every other qubit we've discussed sits still, pinned to a chip, floating in a trap, held in a tweezer. This one is moving at the speed of light. You can't exactly hold it in place.
You can't, and that's the crux of the whole thing. Both the gift and the wound flow from it. Let's take the gifts first, because they're spectacular. Number 1. Remember the entire golden chandelier, the coldest place in the universe, all that machinery to fight off heat. A photon barely cares about heat. It sails straight through a warm room, utterly unbothered by the temperature. So a photonic quantum computer can often run at room temperature. No dilution fridge, no colder than space, just the light. That alone is a staggering simplification.
No fridge at all? After that whole cathedral of cold, that's almost funny.
It's the plot twist of the episode. And gift number 2 is even better suited to something we cared about last time: communication. When we talked about sending quantum information across the world, about unbreakable codes, what carries that information down the fiber optic cables under the oceans? Light. Photons. So a qubit that is a photon is already in its natural traveling form. It's the one animal in the zoo born to fly down a wire and across a city. For a future quantum internet, that's not a bonus, that's the whole game.
Room temperature and born to travel. So, same question I keep asking, what did they give up? Because there's always a wound.
There is, and it's the deepest of the lot in a way. Here's the trouble. Photons are gloriously aloof. They almost completely ignore each other. Cross two laser beams and they pass right through one another without so much as a nod. No collision, no interaction. And that aloofness is exactly why a photon is so quiet and holds its state so well. Nothing bothers it because it engages with almost nothing. But swing back to our two enemies. Computing requires interaction. Two qubits have to be able to feel each other, to become entangled, to do the logic. And photons, by their very nature, refuse to feel each other.
Oh, that's a cruel one. The thing that makes them such good, quiet carriers of information is the very thing that makes them useless at the shaking hands part.
A perfect trap, isn't it? So the photonic people have to resort to wonderfully clever indirect tricks to force an interaction, passing photons through delicate mazes of mirrors and beam splitters and detectors, engineering situations where the mere act of measuring one photon nudges the fate of another. It works, but it's intricate, and a lot of it is probabilistic. Sometimes the interaction happens, and sometimes it just doesn't, and you shrug and try again. And the second half of the wound, because the photon never stops moving, it's genuinely hard to store one. Holding light still, or delaying it until you need it, is its own formidable engineering problem. That's the photonic bargain. Sail through the warm world unbothered and born to travel, but fiendishly hard to make interact and hard to hold in place. The animal that hides the information where noise can't find it.
All right, 4 animals. And I've noticed something. Every single one of them is fundamentally fighting the fragility, chilling it, isolating it, switching it, dodging it. They're all playing defense against the noise. Please tell me the 5th one is different because I want a plot twist.
You've spotted the deepest thing in the whole episode. And yes, the 5th animal is different, and it's the one that makes physicists go quiet and dreamy when they talk about it. Because all 4 we've met so far accept the same basic predicament. My qubit is a fragile thing sitting out in the open, and I must defend it, with cold, with vacuum, with cleverness. The 5th tribe asked a far more radical question. What if you didn't have to defend the information at all? What if you could hide it so well, store it in such a way, that the noise literally cannot find it to disturb it? What if the protection wasn't something you added on top, but was baked into the very fabric of how the information is stored?
Baked in. So instead of building a better vault around a fragile jewel, you somehow make the jewel itself impossible to scratch.
That's the dream exactly, and it's called topological quantum computing. Now, topological is a fancy word, but the idea underneath it is one you already know in your bones. Think about a knot tied in a loop of rope. You can shake the rope, jiggle it, warm it up, wobble it about, and the knot doesn't care. The knot is still a knot. You cannot get rid of it by any amount of local fiddling. The only way to undo a knot is to grab the whole thing and deliberately unpick the ends. The knottedness is a global property. It lives in the whole shape at once, not in any one spot. So no local disturbance, no random poke from the environment can touch it.
And the environment's pokes are always local, always some stray photon hitting one place. So if you stored your information as a kind of knot,
then the environment's little local pokes slide right off it, because there's nowhere local to grab. You've understood it perfectly. The plan is to store a qubit not in the state of any single particle, where one bad nudge could ruin it, but smeared out, woven into a global knot-like pattern shared across several exotic objects at once, so that no single local disturbance can read it or wreck it. And here's the truly beautiful part. To compute, you physically move these objects around each other. You braid them, like plaiting hair, weaving one strand over and under another. The pattern of the braid, the over and under of the dance, is the computation. And because a braid, like a knot, is a global thing, A little jitter in the middle of the dance doesn't change which braid you tied.
So the error protection we spent a whole episode building out of hundreds of qubits and clever software, checking for errors without ever looking at the data, this fifth animal is trying to get for free, built into the physics itself.
That's precisely the promise, and it's why the dream is so seductive. Remember the sobering price we paid for error correction. Hundreds, even thousands of fragile physical qubits sacrificed to protect a single reliable logical one. The topological dream is to have a great deal of that protection handed to you by nature, at the hardware level, before you write a single line of correcting software. A qubit that is robust from birth. If it worked, it might be the sturdiest qubit of them all.
I hear "if it worked" doing an enormous amount of work in that sentence.
It's carrying the whole load, and this is where I have to be completely honest with you, because honesty is the promise of this whole course. Every other animal in the zoo, whatever its flaws, unarguably exists. There are superconducting chips computing tonight. There are ions floating in traps right now. But the exotic objects you'd need to braid for a topological computer, particles that store information non-locally in exactly the way the knot idea requires, are so strange and so delicate that after years of searching, we are still not even certain we can reliably make them and confirm they're really there. The other four tribes are refining machines that work. This fifth tribe is, to a real degree, still trying to confirm that its fundamental building block can be summoned into existence at all.
So it's the longest of long shots. The others are arguing about how to build a better boat. This one's still trying to prove its kind of wood floats.
Haha, that's it exactly. And it's the honest wound, potentially the most robust qubit ever conceived, and also the furthest from being real. The biggest prize on the longest odds. A bet that refuses to fight the noise at all and instead hides the treasure somewhere the noise was never able to reach. 5 bets, 1 dark ocean.
Let me try to hold all 5 in my hands at once because my head's spinning a little. A circuit you print like a microchip. Fast, buildable, but leaky and needing the coldest place in the universe. A single trapped atom, flawless and long remembering but slow and hard to scale. Neutral atoms in tweezers of light, beautifully scalable and flexible, but young and still finding its feet. Photons, room temperature and born to travel, but hating to interact and refusing to sit still. And the topological long shot, maybe unbreakable, maybe not even possible yet.
You've just recited the entire state of an industry, and you did it in 6 sentences. And do you hear what's underneath every one of them? The same enemy, over and over. Isolation versus control. Every gift on that list is a clever way of buying quiet, and every wound is the price that quiet cost. 5 different materials, a circuit, an ion, a neutral atom, a photon, a knot. And every single one is fighting the exact same dragon we met in that episode about noise. That's the unity hiding underneath all the variety.
And I keep waiting for you to tell me which one wins, and you keep not telling me.
Because I genuinely can't. And more importantly, nobody honestly can. And anyone who tells you they know for certain is selling you something. That's not a failure of the field. That's the thrilling part of the moment we're living in. It might be that one of these animals pulls decisively ahead. It might be that different animals win different jobs. Photons doing the communicating between cities, superconductors or ions doing the heavy computing in the freezer, handing work back and forth. It might even be that the eventual winner is some 6th animal nobody has thought of yet.
There's something I find genuinely moving about that. We're so used to technology arriving finished. The phone, the laptop, the sealed box you just switch on. And this is a thing being argued into existence in real time, out of atoms and circuits and light, with the fundamental question of what it's even made of still wide open.
And that's the note I want to end on. Because think about where this whole course began. The very first idea, the thread we said we'd pull through everything. Information is physical. It was almost a philosophy back then, a startling claim that information isn't some abstract stuff floating free of the world, but is always, unavoidably, written into physical things. Well, look at what that claim becomes tonight. It stops being a philosophy and turns into a workshop. It becomes a real atom cupped in a real vacuum by real lasers. It becomes a real circuit at the bottom of the coldest well ever dug. It becomes a speck of light racing down a real fiber. Information is physical, and this, the golden chandelier and the floating atom and the tweezers of light, this is what physical actually looks like when you go and touch it.
The abstract arrow on the sphere, finely made of metal and atoms and cold.
Made of metal and atoms and cold, and built by people, this decade, with their hands. That's the engineering wonder I wanted to leave you standing inside. Not a finished machine, handed down from on high. A whole zoo of half-tamed, extraordinary creatures, each one a different, daring bet on how to hold something as fragile as a quantum state still enough and long enough to do something useful with it.
And that's the question you're leaving hanging in the air, isn't it? You've shown me they built these things, 5 ways, but you haven't once told me how good they actually are. Whether any of them can really do the miracles we spent the early episodes marveling at, break the codes, simulate the molecules, any of it. Or whether that's all still a promise.
And I've dodged it on purpose all night, because it deserves an episode of its own. The most sober, careful, hype-cutting hour in the whole course. We've toured the zoo, we've admired the animals. Next time we ask the ruthless question, how strong are they, really? What has a quantum computer honestly done that an ordinary one couldn't? And how enormous is the gap between the beautiful machines we just met and the world-changing ones we were promised? That's next time. Bring your wonder, but bring your skepticism too. You'll need both.
Wonder and skepticism, in equal measure. I'll pack them both. Until next time.